Uh, Hi everyone, my name is Rinan Dakyo and I will going to report Design Flood Discharge Part 2. So, drainage area and shape-based formulations. So, the aforementioned formulations had the drainage basin variable as the major factor. However, the following formulations take into consideration additional variables such as the shape factor. For instance, Dredge or Bird's formulation is based on Indian records and states that QP equals 19.6 times A over L raised to the power of 2/3, where L is the length of the drainage basin in kilometer. On the other hand, if W is the 35 average width of the basin in kilometer, then substitution of A equals WL into the previous expression leads to QP equals 19.6 times W times L raised to the power of 1/3. So next is rainfall and drainage area based formulation. The original developments of such formulations are from northern USA, Ohio, to connect as QP equals CP times P times W raised to the power of 5 over 4, where P is probable 100-year maximum 1-day rainfall in centimeter, and CP is the flood constant equal to 1.5 for humid areas and 0.2 for desert areas. The formula requires in its application fairly uniform with no storage effect. The application validity of this formulation is confined to areas from 1,600 to 16,000 kilometers squared. If the area is wider at the lower end, the formula gives two small results, and if it is wider at its upper ends, the results obtained are too large. A correction of 10 to 13% may be required for width variation. So next is total runoff and drainage area based formulation. Most widely known alternative to this group of formulation is the Boston Society of Civil Engineers formula, which is suggested by the Flood Committee of Boston Society of Civil Engineers per square kilometer that is based on the New England flood of November 1927. So, QP equals 0.0056 times D over T, where QP is the peak flow meter cube over second over kilometer squared. So, D is the flood runoff total depth in centimeter. And T is the total flood period in hours, or the base of the flood hydrograph. So, next is rainfall intensity and drainage area based formulation. This is referred to as the rational formulation, which is the oldest and best known 36 formula for determining peak flow from a given drainage area. The peak discharge QP formulation is given as follows. QP equals 0.28 times C times I times A. So, QP is obtained in meter cube per second on the base that the rainfall intensity I is in millimeter per hour and the drainage area in kilometer squared. The rational formulation for flood peak discharge estimation has the consideration of the entire drainage area as a single unit. Flood peak discharge estimation at the most downstream point and the assumption of uniformly distributed rainfall over the drainage area. General assumptions in the rational formula are that the predicted peak discharge QP has the same probability of occurrence as the used rainfall intensity. The runoff coefficient is constant during the storm rainfall, and the recession time is equal to the time of rise. On the other hand, in the modified version of the rational formula, A storage coefficient is included to account for a recession time larger than the time the hydrograph takes to rise. Hence, enhanced formulation is QP equals 0.28 times CS times CIA. Next, in a drainage basin, the peak flood discharge is reached when all parts of the watershed are contributing to the outflow at the time of concentration in minutes, which is given by Kerpich 1940 on the basis of main channel length in meter and the slope as TC equals 0.01995 L times 0.77 S minus 0.385. So next is envelope curves. If in a region with same climatological characteristics, the flood record data is scarcely available, then the envelope curve technique is adapted to develop a relationship between the peak flood discharge and drainage area. Envelope curves are very useful in getting quick estimations of peak flood designs discharge values. If equations are fitted to the envelope curves, then it provides empirical flood. Next is engineering water structure design. Any water resource related structural design necessitates the estimation and final decision on the desired discharge value. Although there are different methodologies, each water related problem has its specific formulations and calculation method. So next is debris flow. During floods, these are liquefied, fast-flowing landslide mixtures of unconsolidated water and debris. In arid regions, due to exposition of naked land surfaces to hot and cold diurnal temperature changes, earth surface materials get broken into small masses, which are triggered for movement over slopy regions during and after each storm rainfall and runoff. It is necessary to construct small dams, retaining walls, artificial steering depression, wire network, and similar hindrances against their flow in order to maintain usable structures safely. Debris flow calculation. Next is rock falls. Rock falls and slides involve a sudden rapid slide of bedrock along plans of weakness. Rock slides are very common in the overstepped hill slopes, such as along the case of Al-Hada Road alignment in the Kingdom of Saudi Arabia. Such occurrences are possible at a set of locations along the road alignment. So next is canals. There are necessary artificial engineering water structure collect and transport surface flow to the sea or to any desirable outlet point. There are also used around any town or city in order to protect the settlement and industrial areas against possible flood danger and inundations. The surface water velocity calculations can be made by Manning formulation. Next is groundwater velocity calculation. In the groundwater studies, velocity calculation can be achieved according to Darcy law, where the necessary parameters are hydraulic gradient and 41 hydraulic conductivity. So, gully and sediment yield calculations. Sediment transport assessment in headwater areas of catchments in arid regions is a major concern for flash flood hazard control and watershed management. Under homogeneous conditions of climate geology and land use, the topographic control on erosion and deposition processes play a major role in landscape evolution. According to Lal, 1994, either our conceptual understanding of the erosion sedimentation problem on the Earth's surface is far from being complete, especially in arid and semi-arid regions, or erosion sedimentation research techniques are still more of an art than a science. Sediment yield was studied in the past by two basic types of analysis, namely hydrological and hydraulic approaches. Highway safety assessment and recommendation. Road safety assessments, also referred to as road safety audits and safety literature, are a proactive approach to improving road safety. Maintenance based on the present conditions must be affected when it is possible to assess residual lives of the assets on basis of inspections or test results. The road area must be observed at least weekly or in wet periods, more frequently, say daily, in order to visualize defect occurrences, leading to minor repairs and improvements to eliminate the cause of defects and to avoid excessive repetition of maintenance efforts. In cases of unseen and unpredictable repair requirements, urgent maintenance must be undertaken immediately. It is possible to divert the surface water through properly designed canals and earthworks or vegetation plantation, especially plants with deep root possibilities. Next is flood hazard reduction. In general, within the subtropical climate belt, and hence in particular arid and semi-arid regions are prone to occasional floods due to unexpected weather and geomorphological effects. In addition to these natural effects, the human settlement and urbanization highway network planning may also increase the flood hazard potential due to unconscious or improper planning without flood hazard and inundation maps availability. Under the light of aforementioned information, it is possible to deduce the general and specific recommendation for flood awareness studies, hazards, and inundation areas. That's all. Thank you.